Today we're going to talk about some operations that we can perform with sets and some ways that we can kind of manipulate sets and put them together and pull them apart so that we can do some cool stuff with them. So we're going to start out with some operations. The first one is the union. So the union of two sets, we use this U looking thing to denote it, and U for union, right? So whenever you think of union, our nation being a union, marriage being a union, lots of things in life called unions, right? Unions bring things together. So when we're thinking about this with sets, it's saying, hey, it doesn't matter if you're in A or if you're in B, you're a part of the larger picture. So you can think about it whether you live in Washington or you live in Alaska, you're a part of the union that is the United States of America, right? So that's our deal. So when we draw a Venn diagram, we would shade in all of A, we would shade in all of B, and it doesn't matter where you fall in that, you're in the union of the two sets. So unions, pulling stuff together. U for union, all right? So some simple examples of this. We're not going to take the time now to talk through all of them. Something to note, though, when we put, say, A1 and A2 together in a union, notice that 5 is an element in both of those sets, and that element 5 is only listed once. That's because it doesn't matter how many times an element is listed in a set, there is an element, right? So if something overlaps between two sets and you're taking the union, you only need to list it once. That's our big takeaway, all right? So take a look at that example on your own time. Make sure that you're feeling good about it. Kind of on the other side from a union is this idea of an intersection. Intersections are more exclusive. You think about two roads intersecting, the intersection between the two roads is really only where they overlap, right? Where the roads themselves might be a lot longer. So that's exactly what the intersection with sets is. So you have a set A, you have a set B, and we're looking at where the two meet and what it counts as part of both of them. So in order to be in the intersection, an element must be both in A and B. And we denote this with this thing that looks like an A rounded off with no crossbeam. So I like to think of that as that denotion, right? That A is reminding me that it has to be an A and B. Some people like to think of it as it looking more like an N for intersection, right? So intersection in, or like an A for and. Either way, that's our way of denoting it. That's what it means. So when we draw the Venn diagram here, we're looking at the stuff that's in A and B at the same time. So it's only going to be that little center exclusive wedge. And again, some examples here. A lot of times the intersections of two sets are going to be the empty set. That's okay, all right? Sometimes they are the entirety of the sets. The two sets are the same. And sometimes it's just one of the sets because that set was a subset of the other set. So again, take a look at the example and let me know if you have questions. So when that intersection is the empty set, we say that that intersection is disjoint. So if I think about state residency, say, so people who live in the United States, you can only be a resident of one state. When you go move from one state to another state, you give up residency in the old state and you become a resident of the new state. So all of the residents of Colorado and all of the residents of Oregon, that intersection is empty. There's nobody who is a resident of both Colorado and Oregon. So we say that those two sets are disjoint. So that's one of the things that we can do. We can test to see if sets are disjoint. This matters a lot in statistics and probability when we're thinking about how probable it is that something will happen. And in this class, it'll come up some along the way as well. So, all right, the difference between two sets. You guessed it, right? It's everything that's in A and not in B. That's it, right? So If you take everything that's in A, you take away the things that are in B, you're left with the elements that are in A and not in B. And that's how we read that. So the difference A minus B is the set of all elements X such that X is in A and not in B. All right, so when we draw that, this is the one that ends up kind of looking like a Pac-Man. So we're coloring in everything that's in A, but not that little intersection wedge. All right, and sometimes we write this with this slash, so we have A and not in B. All right, that's what that slash means there. All right, so if we're taking a look at two sets, I have A sub 1, A sub 2 here, and I'm looking and I want everything that's in A1 that's not in A2, then I would start out with A1. And if I were doing this problem, the way I would do it is I would list everything in A1. So I would start out with 2, 5, 7, 8. And then I would go through and I would say, all right, 2, 5, 7, 8. I'm going to cross out any 1s. I don't have any. I'm going to cross out any 3s. Don't have any. I'm going to cross out any 5s. All right, cross out the 5. It's crossed out. And then I'm left with 2, 7, and 8. And that is what my difference there is. And same difference. One of the things that's kind of cool about the difference of sets is it doesn't matter how big the sets are. So in this case, when I'm doing the difference between A2 and A1, so everything in A2 that's not in A1, I'm looking at 1, 3, and 5 as my starting point. And then I go, I'm going to cross off any 2s. I don't have any. I'm going to cross off any 5s. Done. Going to cross off any 7s. Don't have any. Cross off any 8s. Don't have any. So I'm left with 1 and 3 because my 5 was crossed off. All right. So that difference can be taken either way, and you can have things in them either way. It's really neat. All right. So here's another example. All right. So you have sets A, B, and C. All right. And we're dealing with some absolute value stuff. So we have to solve some things to figure out what the sets A, B, and C are. All right. Using interval notation, some fantastic practice here. All right. From looking at what we did last time. And we're going to determine our intersections and our differences and our unions. All right. Solutions there. Check it out. All right, another thing that we can do with sets is we can think about everything that's not in the set. So remember we had this universal set last time, right? So we have the universal set that's all of the things, right? And you get to define how big your universe is. So last time I think we used the example of all the students at St. Martin's, all right, as being a possible universe, okay? So you set that, and then you say, all right, so I have a set A. Remember, you were an element in the set of students taking Math 220 this semester. So you are the set A, and its complement is everyone else in the universe. So here we would have all of the students at St. Martin's who are not taking Math 220 this semester. So everybody who doesn't fit in that set but fits in the universe that we've defined, that is what's called the complement. Notice it's an E, so not complement like we're being nice to each other. It's complement, like they go together. So the thing about this is if you put A and a complement together, then you end up with the entire universe. All right, so there's this beautiful thing where you put the two things together, and even though they were opposites, you put them together and you get everything. So they complement each other very nicely that way. All right. So here another example where you're taking a look at the numbers between 1 and 10 as your universal set. That's what we've defined it to be. And we have a set A and B. B is all the even numbers. If I want B complement, then I'm going to end up with all of the odd numbers between 1 and 9. Right? That's the idea here. You can also do combinations of these operations. So you can think about this part C here, A intersect B complement. All right? So in order to do this intersection, you need to know what B complement is first. So there's a little bit of an order of operations thing happening here. If the complement bar is only over one of the sets, then you need to take that complement first before you do any other operation with it. If the complement bar falls over the entire operation, then you get to do the operation with the complement after. So just think about that a little bit. Think about how order of operations might fall in that. And we'll talk more about that if we need to in class, okay? All right. So onward. Partitions of sets. So a partition of a set is kind of cool. So you take a set, right? And you're going to get a collection of subsets that don't overlap at all. But when you put them all together, you have the whole set. Okay? So if I take A and A complement in my universe U, right? They are a partition of that universe, of that universal set. Okay? A and A complement are. So here's an example where I have A as the numbers between 1 and 7, and I have B is 1 and 6, C is 2 and 5, D is 4 and 7, and I have this S, all right? S is B, C, and D, so I'm going to put all of those things together. So S is a pairwise disjoint collection of subsets of A, because B and C have nothing in common, C and D have nothing in common, and B and D have nothing in common. The thing is, though, if I look at those three sets, the number 3 is missing, right? It didn't get any love there, yeah? So it's out of it all. So if I instead take a look at it and I would throw C at 3 in there as a subset somewhere else, then I would have this idea of a partition. So a partition of a set is when I've got the subsets and they have these 3 properties. So every one of my subsets is not empty, all right? And every set of my subsets, every pair of my subsets, they're not the empty set, or sorry, their intersection is the empty set, so they're pairwise disjoint. And if I put them all together, then I've got A. So going back to this example here, if I had just added in E, that was the set containing 3, that would have been a partition of my set A there. All right, so in case that wasn't super confusing, let's try an example of this. All right, so we're going to take a look at, I have a set A. This time I'm going to go with just numbers 1 to 6. All right, so I take a look at S1. S1 is a collection of subsets, all right, which is what a partition is. So we're doing good there. There's no empty sets in it, so that's good. So I have 1, 3, and 6 as one of them, 2 and 4, and then 5. If I look at the intersections, if I look at 1, 3, 6 intersect 2, 4, nothing in common, empty set. 2 and 4 intersect 5, again, empty set, pairwise disjoint. And I look at the last possible one, 1, 3, and 6 intersect 5, disjoint, all right? So S1, all right, as long as all of the elements in A are accounted for in one of those subsets, so I have all of them there, S1 is a partition of A. Now, if we take a look at S2, in S2, one of the things that's in there is the empty set. As soon as you see the empty set as part of the list of subsets, you know it's not a partition, all right? You don't have to check anything else. You can just be done. There's an empty set in there. It's no good. All right, taking a look at S3 there, I have no empty sets, so I have to move on. I have to check something else. So then I check for pairwise disjoint. I have 1 and 2, and then I have 3, 4, and 5. Those are good. I have 1 and 2 paired with 5 and 6. Good. 3, 4, 5 paired with 5 and 6. They share a 5. The intersection is not empty. So subset 2 here and subset 3 here, right? in my set of subsets, right, S3, they're not pairwise disjoint, and that makes this not a partition. And finally, looking at S4 here, no empty sets, so I have to check other stuff. Pairwise disjoint, 1 and 4 and 3 and 5, nothing in common. 1 and 4, 2, nothing in common. 3 and 5 and 2, nothing in common. Good. Then I have to check and make sure that I have everything in A represented. I have a 1, a 2, a 3, a 4, a 5, 6 is missing. So S4 is also not a partition. So of these 4 options, S1 is the only one that's a partition. All right, so I am going to leave it to you to take a look at example 23 here. And again, we'll talk about it in class if we need to. All right, so more solutions. All right. And finally, the Cartesian product. This is the cool way of putting sets together. And you've been doing this for a very long time. You might not realize it, you might not recognize it. Hopefully you recognize the word Cartesian. You've probably heard Cartesian as the Cartesian plane, the XY plane, where you graph a whole bunch of different lines, right? Yeah, where you do point slope, all that. All right, so Cartesian product of 2 sets. I take a set A, I take a set B, and I write an ordered pair where the first thing came from the set A and the second thing came from the set B. That's all it is. The orders of these pairs matter because it tells you which set things came from, right? So the first element in your ordered pair always has to come from the first set in your Cartesian product. So I have A first in my Cartesian product. So A is coming from A and it's coming first in my ordered pair. B is second in my Cartesian product. So lowercase b as an element of B is coming second in my Cartesian product. Order matters on these. That's why they're called ordered pairs. All right. So that is the Cartesian product. If A or B, either one, are the empty set, then I've got nothing to use for my first entry or my second entry, depending on which one's empty, right? Which makes the entire Cartesian product be the empty set as well. And there's this cool thing that if you think about the cardinality of the Cartesian product, I have whatever the cardinality is, elements in A, that I can pair up with whatever the cardinality number of elements in B is, and I can pair them up in any way I want. So I have the product of the cardinality of A and the cardinality of B, and that is the cardinality of my Cartesian product. All right, and here's an example of A being the set that contains X and Y, B being the set that contains 1, 2, and 3, and then I can take Cartesian products, and it depends on which order they're in what'll come first, letters or numbers. You can also take Cartesian products of sets with themselves. All right, so I can take Cartesian product of A with A, and I can take a Cartesian product of B with B as well. All right, so that is the basics of things that we are going to do with sets in this class, and we'll work everything else that we do off of those things. So I'm looking forward to talking about this all with you.